the world you are viewing this from. As Max has mentioned, this is lecture 5 out of 8, and this is webinar number 4 out of 6. And the message in the purple box, I've mentioned this before, but the materials that I have prepared and are graciously loaded onto the IRIS web pages is intended for educational purposes for undergrads and grads and those that teach them. And so it's not for people who are already employed. Okay, and just a reminder, this is the second course that I've done through IRIS. The first one, Geology and Geophysics in Petroleum Industry. As I'm talking, if you don't know how to get there, the path is here in the yellow box with the red letters. Those have 34 lessons. And then we're doing the second course now, Petroleum Exploration. It will have a total of 8 lessons. And all 8 of these lessons are currently online. So if you want to look ahead, you are able to do that. And the web address is also shown here. So the web address for the first class, again, is down here at the bottom. With today's lecture, we'll be talking mostly about reservoir rocks. And if you want more details, lesson 8 in the G&G course would be a place where you could go and learn some more. And then for the exercise, and I'll introduce the exercise today during our live session, we'll talk about some seismic attributes. And there is a lesson in the G&G course on seismic attributes. So I think this is the third time I've shown this. In order to have success, we need 4 essential elements. Source rocks, which we talked about in our last session on Tuesday. Reservoir rocks that we'll talk about today. We also need sealing rocks or sealing mythologies. And then we need our intervals of interest to be buried deep enough that hydrocarbons can be present. So we talk about the cover, if you will, as the overburden rocks. And then we have 2 major processes that we need. One is trap formation. It could be a structural trap solely. It could be a stratigraphic trap. It could be a combination structure and stratigraphy. And then we need processes related to hydrocarbon, generation of hydrocarbon, the migration of hydrocarbon, and then the accumulation of hydrocarbons. So what is a reservoir rock? It is one from which oil and gas can be extracted using wells, and we can bring those hydrocarbon fluids or gas up to the surface. At least in conventional field, what we are looking for are rocks that have 2 primary properties. One is porosity, which is the void space between the rock grains, and that's where the fluids or gas will live. And then we need sufficient plumbing so that the hydrocarbons can escape from the rock, and that's what we call permeability. So porosity, you can think of the pores. Permeability, you can think of how connected or not the pores are. So porosity, it's symbolized most commonly by the Greek letter phi. It measures the void or the empty space in a material. And so it can go from 0%, and really we have to have grains. So although Wikipedia says up to 100%, typically rocks can get porosities as high as the low 30s, so maybe 32%. And that would be at the time of deposition. As we compact the rocks and bury the rocks, we're going to lose that porosity fairly quickly. And permeability, it's symbolized by the Greek letter kappa or K. It's the ability of a porous material to allow fluids to pass through it. And so there's a little bit of a diagram here. No pore space and no permeability on the left. In the center, the pores are represented by the blue, the grains are the brown. So we have some pores, but they're not all that well connected, so not all that permeable. And then on the right of the 3 we have a lot more pore space, and we can see a lot of interconnectedness. So this would be a high porosity, high permeability rock. The types of reservoirs, I'll mention a little bit about conventional reservoirs, and we have two: clastic reservoirs and carbonate reservoirs. And conventional means that we can use what we might say are traditional or time-tested methods to extract hydrocarbons from rocks that have good porosity and permeability. In the last 10 years or so, there's been a lot of emphasis on unconventional reservoirs. Some people call these resource plays. They're tight oil sands and tight gas sands. They're shale oil and shale gas, and also coal bed methane. And these rocks are much tighter, much lower permeability, and so we need new methods to extract the hydrocarbons from what we would consider, in a classic sense, non-reservoir quality rocks. So if we look at the conventional, further subdivided into the clastic, we might have aeolian fans or alluvial fans, aeolian dunes. We can have fluvial sands, we can have nearshore sands, we can have delta sands, we can have deep water sands. If you go to the G&G lecture that I mentioned earlier, I have a couple of slides on each of these. For today, I'll just look at two, the delta and the deep water, just to give you a feel for some of the things that we're interested in. So river delta, again, a definition from Wikipedia. I think everyone in my audience probably understands a little bit about deltas. They form where a major river meets a ocean or a sea or an estuary. The image here, a NASA image, is of the Mississippi Birdfoot Delta, where the Mississippi has left the coastline and is depositing a big lobe that is currently active. And so the things in green on here is above sea level, at least part of the time, and probably some of it is submerged when we have major storms. The figure on the right shows the position of different delta systems for the Mississippi in the past. The current Birdfoot Delta is over here, but we get delta switching, and so where the river meets the ocean can vary along the coastline, somewhat like if I have a garden hose in my driveway, I turn on the water, that hose can oscillate back and forth and get different parts of the driveway cement wet. We talk about different environments of deposition. The acronym or code that I use for environments of deposition is EOD, and the plural EODs. This is a diagram of the Nile Delta, so the Nile River depositing water and sediments out into the Mediterranean. We have the fluvial part, which would be down here in the south. Then in the light brown is the delta plain. That is the area that would be very close to sea level. It would be severely exposed most of the time, except perhaps in a major storm event like a hurricane. The delta front in the brighter yellow, that's the area that would be affected by changes in tides and certainly by major storms. If you think about beach type deposits, that's what we would expect in a delta front environment. The delta slope, the paler green, that would be where the seafloor gradient is probably on the order of 1 to 3 degrees. That's in terms of a continental setting, that would be the continental slope. And then the darker green is the basinal or abyssal plain type of environment. I'm going to show a cross section A to A prime, and that's here. So this is up dip for the Nile river system. That would be to the south, and then this would be to the north where the Mediterranean is. And you can see these different facies bands, the delta plain, the delta front, the delta slope, and the basinal. And as time progresses and the river builds further and further out into the sea, we see a time transgressive movement of these different facies belts. One thing to note is that the yellow, the delta front, is where we would expect our best reservoir quality, because the tides and the storms are able to put all of the sediment in suspension. The finer material will get winnowed out, drift out further into the basin. The coarser material will not move as much. And so this is an environment in which we have fluctuating wave base and storm base. And this is where we can clean up the rocks, get well-sorted rocks with good porosity and good permeability. The delta plain can be a reservoir quality rock, but we would not expect it to be as good as the delta front. And that'll come in when I start talking about the exercise in a few minutes. Here's a seismic example. You can see in the background the black and white of the seismic reflection cross-section, and superimposed on that, I've shown some interpretation. The delta plain would be the brown color coding. The delta front, again, you can think beach or near shore, that's in the yellow. The slope, and then the basin. And then there's a couple of orange bodies out here. Those are what we would call deep water fans, deep sea fans, TOA slope fans. And I'll talk about the fans, the deep water fans, in a minute. So the deep water fans are formed of turbidite deposits. Turbidite is a geologic deposit that results from a turbidity current. Sediment moves down a slope due to gravity, and it can distribute a fair amount of clastic materials, usually making use of canyons on the shelf, and then those canyons can also cut into the slope, and then at the toe of the slope where the seafloor gradient flattens out, the turbidity currents lose their velocity because the gravity pull is not so large, and the coarser materials deposited first, the medium grain, and then the finer grain. And so we can get a lobate shaped deposit near the toe of the slope. So this is a diagram, three-dimensional representation. This would be a continental shelf, a slope, and a basin. We can have periods of time when the river's down cut. We'd have mostly erosion of the canyon and the upper and mid slope. We can get deposition as the gradient shallows and the turbidites slow. And so we can get confined sediment up in the lower part of the slope, and that's represented here, where we have a cut into the previous deposits, which are gray here. And as that turbidite, mostly water, but with sediment grains mixed in, flows down there, the heavier, denser material will be near the axis of this canyon system. Finer material may fluff over the banks. As we get into the basin, where the seafloor gradient gets very gentle, we don't have any confinement, any erosional cut. The flows are going across the basin floor, and again, the coarser material will drop out closer to some of these distributary channels. The medium and finer grain material gets sorted to be deposited further away from the distributive channels. So we can get reservoir quality sands during periods of turbidite deposition, which are largely associated with low stands of sea level in the continental slope and out into the basin floor near the toe of the slope. So if we have a area and we've done some seismic mapping, this is an example from the Gulf of Mexico. The pink are representing salt bodies, and so we have a salt wall here, we have a salt wall here, and we have a little place where the salt is not preventing turbidites to get through. We have a shallower mini basin, and when that fills, it will start to spill sediment into the next deeper mini basin. With 3D seismic, we're actually able to image some of these distributary channel systems. And so if we were to see something like this, we would use a depositional model such as this one. And if we're in the upper parts where it's a little bit more confined, we might think we're in the upper part of this conceptual model. And in this conceptual model, if I drew a cross section here, you can see how the sands are distributed. The better reservoir quality are the yellow sands. The moderate reservoir quality are the orange sands. And if we're out where we see more of the distributive unconfined sediments, that would be in this part of the depositional model. And if I drew a cross section through that, it would look more like this. Thinner sand lenses, but they can extend over quite a large aerial extent. We can also, let me go back. We can also, in a conventional field, have carbonate reservoirs. And I could certainly spend a lot of time talking about carbonate reservoirs. I'm just going to use this depositional environment diagram. And so we could have reefs near the edge of the shelf. We could have oolitic shoals. We can have tidal channels, tidal flats. So there's a variety of conditions under which we might expect to get carbonates that have either initial or post-depositional high porosity and high permeability that can form a reservoir. Here is a satellite image of South Florida. So here's the Florida Keys that got hammered this year by some massive hurricanes. And so this is a carbonate environment in which we might get some future carbonate reservoirs with good porosity and good permeability. So let me mention just a little bit about these unconventional reservoirs. They do not have high porosity and high permeability, but they can still hold a good amount of oil and or gas. The difficulty is trying to get that oil and gas out of the rocks and up to the surface where we can utilize them and sell them. So here's an example of a conventional reservoir that might have a porosity of 20 to 40%, high permeability. We can drill into these and we can produce hundreds to thousands of barrels per day through standard drilling operations and standard pipe. Moderate porosity might be in the range of 10 to 20% with some moderate permeability. A well in this type of a reservoir might produce a few tens of barrels to maybe a couple of hundred barrels a day. And on the right, this is a slide with the example from a Marcellus shale up in the northeast United States. Ultra low porosity, 2 to 10%, and ultra low permeability. These can hold hydrocarbons, but the hydrocarbons will not flow under natural condition. And so what we have to do is we have to stimulate the rocks or fracture the rocks. And if we do that, we can produce on the order of 10 to maybe 100 barrels per day with the fracking involved. So the unconventionals have become important to us in the last 10 years because of two main technological breakthroughs. One is horizontal drilling so that we can get a well that goes through the Marcellus, not just vertically or at a high angle, but it can run along the layering of the Marcellus. And so we can have a well with a mile or maybe 2 miles that it stays within this organic rich source rock that's also our unconventional reservoir. And the other technology is fracking or artificially stimulation or using pressure to cause the Marcellus or other unconventionals to fracture and allow the hydrocarbons to escape. So there's several slides that I borrowed illustrations from. So these are the references for the different illustrations, slide 4, 5, 9, 11, 12, 15, and 16. So that's what I have prepared for the lecture part. We'll pause here for a few minutes and see if there are some questions. And then what I'd like to do is move into the introduction to the exercise. And if you are able to do the exercise, that would be great. If not, I think it's worth your while to stay tuned for a few more minutes and hear what the exercise would cover. So Max, if there are some questions, please pass them on to me. Yeah, and if you haven't done this before, you can use the chat portion of the GoToWebinar control panel to type something in that will appear on Max's computer, not mine, and then Max can relay that to me over the audio links.
Yeah, no questions have been posted so far, but I was curious if you can kind of get a sense of the permeability and porosity of the stratigraphic unit by looking at the 3D seismic, or?
What we would do with the seismic, and it comes out a little bit in the exercise, we'll try to figure out the environments of deposition. And so if I know my field is in a location where for my target interval it was fluvial rocks, we could then look in a database that most companies would have. What sort of porosities and permeabilities would I expect if I have fluvial rocks that are, let's say, Eocene in age and at a depth of 9,000 feet? And so what we try to do is understand the environments of deposition, and then we can use analogs or a database to say if in fact it's a fluvial sand or an aeolian sand or a deep water sand, it has a certain age, a certain depth, maybe something about temperature and pressure, then we could see what is a reasonable estimate of the porosity. Permeability is much more difficult to determine, especially if we only have seismic data. Sometimes people will use a relationship. If I have a rock of a certain porosity, then the permeability should be in a certain range. But the relationship between porosity and permeability is not a simple one, and it's not a universal one. Good question. Thank you. Okay, let me talk about exercise 5. We're back to looking at our Barracouta lead, something that's interesting. What we want to do in order to try to mature this lead into a prospect is consider the reservoir and what sorts of environments of deposition do we think we had at the time that our reservoir unit was being deposited. And our reservoir, if you've been listening in and maybe doing some of the exercises, is early Oligocene. And so we have an estimate or guesstimate of what the age is. And what we want to try to do is figure out whatever we can about reservoir quality, and what we're going to use as our data set is a 3D seismic. And so we'd like to understand both the vertical and lateral stacking of the environments within the upper Latrobe, which is our targeted reservoir. So we anticipate from our regional study and from the outcrops of the early Oligocene and wells that have drilled through the Oligocene, 3 types of reservoir sands. We're expecting that there might be fluvial sands. You can think about point bars as an example, delta plain sands, and delta front sands. So reservoir quality, porosity, and permeability will vary based on the types of sands or the environments of deposition. So reservoir quality is increasing. It can be good for fluvial sands. It would be a little bit better if we're in a delta plain environment, and the best reservoir quality we anticipate occurring where we have delta front sands. So the question is, can we use seismic data to determine where these three types of sands or environments of deposition exist just below the top of Latrobe, that should be TOL, unconformity, and deeper within the upper Latrobe reservoir unit? And I would say yes, I think we can use seismic attributes to figure some of these things out. So in the exercise, you're going to make an environment of deposition predictions using our targeted interval that we have subdivided or cut or sliced into 6 proportional slabs. And I'll show you an example on the next slide. Each of these slabs will have an equal thickness. We'll look at each of the slabs and we'll look at an attribute that's the absolute value of the amplitude. And then we'll see what sort of aerial distribution this seismic attribute has. From our land data, our outcrops and our wells, we're expecting that our blocks should have fluvial and delta plain sands. It may get into delta front sands. And so here is an image from my 3D seismic data. It is a time slice at 1,000 milliseconds, or this is what the data would look like if you looked at 1 second two-way travel time. 1 second is 1,000 milliseconds. And so north is shown here. And so we're looking, if you will, at a subcrop of the seismic. And the next slide, we'll look at this inline 1915. Let me explain what this time slice is showing me. It's showing me the seismic amplitude values. And if you have listened to the earlier lectures, we have deduced that when we have the reservoir interval, the upper Latrobe, it's going to have strong amplitudes. The blues would be a black on a black and white section. The reds would be the whites, and the zero crossings would be the shades of white. So I'm getting blue blues and red reds. That's high amplitude. And so this is probably my reservoir. The overlying unit, the lake entrance formation, is largely deep water shales, fairly similar velocity and densities, and so we don't get many seismic reflections. So this lower amplitude, the light red to the light blue, is the signature we'd expect for the overlying lake entrance the lake entrance formation. So the top of Latrobe unconformity would go around something like this, separating the higher amplitude response from the lower amplitude response. There are some blacks in here, and that's some coherency data that I have co-rendered. The coherency data tells me where there are abrupt changes in the seismic response. And so you can see a little bit of a black lineation going through here, and that's a small offset fault near the crest of the anticline. You can think of this as bathtub rings. So when we have these elongate bands of reds and blues, that's telling me that I have an anticline. And so the shallowest point of the anticline would be within this blue. So this little red here and this little red here are probably the highest points, at least in two-way travel time, for the Barracouta anticline. And then I go down the flanks, and then the reservoir, the upper Latrobe, would be on deeper time slices out here, and I'm into the younger overlying lake entrance formation where it's the lower amplitude. So here is that inline 1915. The red is the top of the Latrobe unconformity, which is equivalent to the top of my reservoir. The cyan is the base of the reservoir interval. What I've done, I've hit the click button a little too soon. I'm going to redraw this, and I'm going to flatten it so that this cyan horizon is horizontal. And so what I'm trying to do is take out post-depositional structuring and tilting. And so this is the same seismic, but I've shifted all of the traces up and down, so my base reservoir cyan is now flat. And so now I can look at the thickness variations and other variations within the upper Latrobe targeted reservoir interval. Now I'm going to use some software tricks to do something else. I'm going to take that flattened section, and I'm going to ask the computer, look at the interval from red, the top of the reservoir, to cyan, the bottom, and at each location divide it into 6 equal units, and then put a horizon at each of those boundaries. So I have 6 intervals. The oldest at the bottom is 1, the second 6, the third 6, the fourth 6, the fifth 6, and the sixth 6. And now for each of these 6 intervals, I can extract different seismic attributes. So everyone should be familiar with seismic amplitude. It's the excursions to the left or right of 0 that's telling me of the reflection values, and that's related to how big or small impedance contrasts are. And some of the values are positive, or excursions to the right, some are negative. The seismic attribute that I'm interested in is seismic magnitude. And what that is I take all the seismic amplitude numbers, positives and negatives, and I take the absolute value. So if it's a negative number, I multiply it by a -1. If it's a positive number, I multiply it by a +1. And so all the amplitudes are now positive numbers, and the maximum excursion is not necessarily related to positive excursions to the right or negative excursions to the left. So the magnitude is telling me how much reflection energy, if you will, there is at each location for each of the time samples. So what do we expect? If we're in a fluvial environment, at the scale of the seismic data, we'd expect to see large lateral changes, as maybe we would go from a point bar into an overbank into a area in between fluvial channels. So I'd expect to see maybe moderate to large amplitudes, but the amplitudes would be broken up. They would be discontinuous. In a delta plane, those sedimentary bodies would be more widespread, and there would be less local variations, so the reflectors wouldn't be quite as broken up or disjoint. In a delta front, where we have storms and tides reworking the sediments, we would expect the rocks to be fairly similar in their seismic characteristics over fairly wide areas. So we're thinking fluvial is going to be more variable in the seismic response, more disjoint. Delta plane would be intermediate, and delta front, we'd expect to see fairly continuous, uniform reflectors. Now, this is the shallowest, the youngest of these 6 slices that I've made, and the colors here are the magnitudes, and the blacks here are faults that cut into that. The yellow is where we propose to drill. And so you can see that this is fairly uniform and kind of moderate to low amplitude. This is more continuous. The color variation is less. And over here, we get a whole hodgepodge of different amplitudes. And so in the exercise, I've given you the interpretation that there's a boundary probably through here, separating the more continuous reflectors from the moderately discontinuous, and another boundary, the moderately discontinuous to quite discontinuous. And so the interpretation is that we go from fluvial deposits to delta plane deposits to delta front deposits. There's something interesting in this slide as well, you can see it right here quite nicely. This kind of wraps around somewhat like those red and blue bands did on my time slice. It turns out that that's the extent of hydrocarbon in the Barracouta field. We call this a direct hydrocarbon indicator. It's easier to see here because of the contrast is a little better, but with some detailed work, you can map this thing around. And so the fact that I have a hydrocarbon indicator on my Barracouta structure gives me more confidence that there is hydrocarbon there. Now, how does this response come about? It's because the sands in the upper Latrobe in this area have hydrocarbon in it, mostly gas. The same sands over here in the pore space have brine or seawater in it. And the acoustic properties of a sand-filled sand, a water-filled sand or brine-filled sand is different than the acoustic seismic properties of a gas-filled sand. Similarly, here and here, although it's a little more difficult to see. So what you would do in the exercise, you have this sixth slab or proportional slice interpreted for you. The exercise has the other 5 slices color-coded like this, and it also has the boundaries. And so what you can use is a piece of tracing paper. You can trace where this cyan boundary is for each of the 6 slices, where the yellow boundary is for each of the 6 slices, and you can figure out how these environments have shifted back and forth through time. If we drill right through the top Latrobe unconformity into the uppermost part of the upper Latrobe, we would expect delta front type of deposits here, and that's going to be our best reservoir quality. We're going to expect delta plain types of sands here. That's an intermediate reservoir quality, and fluvial sands over here. That's good, but not as good as the others in terms of reservoir quality. So you can look at how these facies bands migrate through geological time. I'm a bottom to top geoscientist, so I like to think about what was happening, and then the second was laid down, the third was laid down, the fourth, the fifth, and the sixth. And so you can look at these slices and how they vary, and you can talk about times of transgression, times of regression, and you can understand a little bit better how the reservoir quality might vary across the field and as you go through different intervals within the target reservoir represented by these six proportional slices. So that should be enough to whet your appetite, and I hope some of you will have the time to go through some of these exercises. I think you can maximize your learning by doing the exercise, and then the IRIS website also has exercise solutions, so you can see what a seasoned veteran like myself would come up with. So we'll conclude for now and have some questions. Just a reminder, next Tuesday we'll have our 5th of the 6 webinars. I'll talk about estimating ultimate recovery, that's abbreviated EUR, and then we'll talk about maturing a prospect, the steps that we go through to try to get ready to present to management a candidate to drill an exploration well. And next Thursday, a week from today, we'll have the last lecture. That's on what I would recommend you would include in that type of a management review where you're trying to get permission to drill an exploration well in the area that you've been laboring over for 4 or 5 or 6 or 12 months. So Max, if there are any questions, I'd be happy to try to answer them now.
I don't have any.
Okay. So the old saying is either I explained everything so well that there's no questions, or I did such a poor job that nobody even knows how to formulate a question. But that's okay. So I guess we will wrap up today's session. Thank everyone for joining. Thank you, Max, for being our coordinator and organizer. And we will see you next Tuesday, hopefully.
That's right. Thank you, Fred, and we'll see you for the next webinar.
Okay. Have a great day, everyone.